Okay, let's talk about scientific notation because scientific notation also involves exponents. With our base 10 system, we can write 10 to the a power as a number 1 with a zeros after the 1 and before the decimal if a is greater than 0. Similarly, we can write 10 to the a power as a number 1 with zeros after the decimal and before the 1 if a is less than 0. What does that all mean? This is summarized in the table here. So actually this is all to do with our place value system. Our place value system, let me actually just get another piece of paper really quickly, and you can take out another piece of paper if you'd like to too. Let's just talk a minute about place value, which is basically the same thing we have going on in the table. So when we have our place value system, we have our decimal. Our decimal does not count as a place, but we have places before the decimal are all whole numbers. And then after the decimal are all the decimal places are all fractions. Same thing as fractions. Who can remember what the place value is right before the decimal? Oh yeah, I was listening to you guys. Ones, tens, hundreds, thousands, 10,000s, right? 10,000s, 100,000s, 100,000s, and then millions. Okay? So what we're talking about when it comes to exponents, 10 is worth 10 to the first power, correct? 100 is 10 times 10, or 10 to the second power. So 100 is a 1 followed by 2 zeros. That exponent of 2 tells me to put 2 zeros there. Actually, it does. Well, I mean, in essence, it does, right? 1,000 is going to be times another 10. That's 10 to the third power. 1,000 is 10 to the third power. That's a 1 followed by 3 zeros. 10 to the fourth power, if I multiply by another 10, that's 10,000. 1 followed by how many zeros? Four zeros. The exponent tells me the number of zeros. 10,000 has 4 zeros. 10 to the fifth, a million is 10 to the sixth power. And you can actually see that with your comma every 3 places. So since there are 6 zeros, a million is a 1 followed by 6 zeros that has 2 commas, right? Who can tell me what is, if we're using, we call our place value system a base 10. Why do you think it's called base 10? Because the base is a 10, base 10. Okay, what about 1? 1 is 10 to the, you see the pattern, 6, 5, 4, 3, 2, 1. Oh, we said that anything to the 0 power is the same thing as 1. Okay? Now over here, our decimal places, after we're going down, going up, we're multiplying by 10. Going down, we're dividing by 10. What's 1 divided by 10? 1/10. 1/10 is 10 to the negative 1 power. That's a tenth. Then over here you have hundredths. That's 1 over 100 is 10 to the negative 2 power. What do you think about a thousandth? Thousandth is 1 divided by 1,000, or 10 to the negative 3. 10,000th, 10 to the negative 4. 100,000th, 10 to the negative 5. Millionth, 10 to the negative 6 is a millionth. So if you think about, okay, a million is 10 to the 6th power. A millionth is 10 to the negative 6. That's the whole thing about the negative exponent means the reciprocal, right? Would you rather have a million or a millionth? Oh, a million. So you'd rather have a big number. All your big numbers, your really big numbers, are going to have very big exponents, okay? Remember when I was doing the problem something like this, 2 to the let's say 100th power to the 100th power. What would that be? 100 times 100 is, it's like 10 squared times 10 squared is 10 to the 4th. That's 10,000. 2 to the 10,000th power. Do you think that's going to be a really big number? In fact, it is. If I go 2 to the 100,000th power, oh, actually, it's even too big for my calculator to handle. I was going to use a really big number, but okay. Let's just go 2 to the 32 power. Let's try that. 2 to the 32 power. Even bigger. 2 to the 50th power. Trying to get that sweet spot, right? So 2 to the 32 power was really big. What do you guys think about this number right here? 2 to the 50th power. Is it really only 1.1? And you guys, if you're talking over there, it's distracting to everyone, including me. You guys that don't. So the problem is the calculator doesn't have enough room to put that huge number. And we could see that 2 to the 32 didn't even go over. What I was looking for is for a number to be written in scientific notation. Because if I say I have 5, let's just say in my bank account I have 5 times 10 to the 6. How much money do I have? I really don't have that much money, you guys. But how much money would I have if I have 5 times 10 to the 6? 5 million. That's 5 million because 10 to the 6 is always a million, right? This is 1 times 10 to the 15th power. Well, if we keep going, right, if I go 10 to the 7th, that's going to be 10 million. 10 to the 8th, right, that's going to be 100 million. 10 to the 9th is going to be a billion. If I count by threes, 10 to the 12th is a trillion, right? That's going to be a 1 followed by 12 zeros. 10 to the 15th is a quadrillion. So essentially 2 to the 50th power is the same thing as a little over 1 quadrillion. That's way bigger than our national debt, thankfully. Okay, so the point is that when you have really, really, really big numbers, your calculator has to deal with them in scientific notation. What if I took 1/2? Oops, I need parentheses. Parenthesis, let's just do 0.5. 0.5 to the power of 50. That's basically 1/2 to the power of 50. Okay? Oh no. I get 8 point, well, that seems really big. 8 for 1/2? No, but look at this. 10 to the, what's the power on the 10? It's actually a negative 16. You see the negative there? Because if I take 1/2 to the 50th power, that's going to be a really, really, really small number. We already saw that 1/2 to the first power would be 1/2, 1/2 to the second power would be 1/4. It's getting smaller and smaller and smaller. That's the same question, the Cookie Monster question. If he ate the cookie, half and half of half of half of half, if he took on the 50th day, right, he's going to have let's just round it to 8.88 times 10 to the negative 16th power. Well, already negative 6 power, 10 to the negative 6 power is a millionth. So this is probably like what, 10 quadrillionths? 10 quadrillionth, yeah. For the negative 16th power, are you kind of seeing that pattern, the negative and positive exponents? So really small numbers can be written in scientific notation because you don't want to actually have to have all those decimal places, okay? You just don't have room for them on your calculator. So a number is written in scientific notation if it's written in the form C, and C is always going to be 1 digit. It's going to be a decimal place, usually a decimal number, right? So 1 digit in front of the decimal. That's what it means right here when it says C is between 1 and 10. Okay? Where A is an integer. These are all integers. 0, -1, -2, -3, -4. And C is any real number. So it's a decimal number. It always means that we're going to have one digit before the decimal. Okay? This notation is really helpful with really large numbers, like 5.972 times 10 to the 24th power. We already know that 10 to the 6th power is a million. So 10 to the 24th power is, 4 times as large. No, even more than that. 10 to the... Why am I stalled? Okay. 10 to the 18th times more, right, than your million. So this is the mass of the Earth. It's also really helpful for really small numbers. So 2.5 times 10 to the -8th millimeters is the radius of a hydrogen atom. Can you even see a hydrogen atom? No, tiny, okay? So scientists use this because if they're, even if let's say, well, one time somebody owed me money, okay? This is how much money they owed me. And I accidentally said this. I mean, that's only a difference of a 0, but you guys get how profoundly different that is, right? If someone owes you $1,000 and you accidentally say, actually, you owe me $11,000. That's a big difference, and that's only 1 0. Imagine if I'm a scientist working all hours of the night and I misplace 1 0. That has 10 times the effect, right? It's always going to be times 10. So that's why it's really helpful to be able to write these numbers in scientific notation. If we write this in scientific notation, we're going to take the decimal, which exists after the 4, and we're going to move it so that I only have one digit, 1, 2, 3, one digit in front of the decimal place. Since that's 1,000 and I moved the decimal 3 places, it's going to be times 10 to the 3rd power, right? Okay, so I take the decimal on the really big number. I move, where is the decimal here? I don't even see the decimal. Where is it? Yeah, it's at the end. I'm going to move it 3, 6, 7 places. 1.025 times 10 to the 7th power. Now, I know that the numbers are really big if they have positive exponents. If they have negative exponents, they're going to be really small. So here, I'm going to move the decimal 1, 2, 3, 4 places. 5.3 times 10 to the negative. How many places did I move it? 1, 2, 3, 4. Here, I want to move it so that I only have one digit in front. I'm going to move it between the 7 and the 3. 7.325. How many places did I move it? So I have 10 to the -2. The negative exponent tells me I have a really, really small number. Okay? Now, how do we put the numbers back? From scientific notation, I want to put them back in standard form. I don't want to know that I have 5 times 10 to the 6th power money in my account. I want to know that I have $5 million. I don't really, though. So, just so you know. Okay, so how many places am I going to move the decimal? 9 places. It's already taking up. I already have 2 numbers taking up 2 of those places. So how many zeros will I tack on to the end? 1, 2, 3, 4, 5, 6, 7. Every 3... I could put commas if I want. 9 billion. Because 10 to the 9th is a billion. Right? How am I going to put this one back into standard form? I have to move the decimal how many places? 4 places. I already have 2 of them taken up. 305. So how many more should I put on? 2. Okay, there's 30,500. The negative exponent tells me that the number is going to be really small. The 8 already takes up. I'm going to move it 1, 2, 3. If I put a 0 in front, then I can put 3 zeros. If I put a 0 in front of the decimal, which is more proper, I think. Then I can put in those 3 zeros. Do you see what I'm saying? The 3 zeros that come from the -3 exponent. If I put in 6 zeros, 1, 2, 3, 4, 5, 6, and I put a decimal after the first, then I can just write all the digits. Because I'm moving the decimal 6 places, right? But the 1 takes up one of the places, so if I put a 0 in front, then I can just use the 6 zeros. Does that make sense? Yes? Okay, scientific notation. Now for these ones right here, the last two, I would even just suggest you use your calculator. I mean, you could go, okay, 5 times 6. You could do it by hand too, but let's just use our calculator for now. So 5 times, I'm just going to show you how to use your calculator for this, times, and you can actually see some of your calculators do have this 10 to the x, but it's the same thing if I go 10 to the 4th power. And then I'm going to multiply times 6 times 10 to the 8th power. And that's should give it to me right away in scientific notation. You see that? If it didn't have it in scientific notation, you could write it in standard form and then. Okay, so here we have 8. These are all just being multiplied. 8 times 3 times 10 to the -3, so I have to do my little caret here to the -3. And since I don't have any parentheses, it shouldn't multiply just by that exponent. So then times 10 to the -2. Oh, syntax error. Okay. Let me try that again. Oh, what did I do wrong? Oh, I didn't put the exponent to the -2. So it's giving me the number 1, 2, 3, 2, 4. Now remember this is, so I can put, how will I put this back into scientific notation? Does anybody know? Move the decimal. Yeah. Well, I'm going to move it between, I want to have 2.4 as my answer. So 1, 2, 3, 4. Times 10 to the -4th. Yeah? Well, I just rearranged the numbers. I could do it in any order because you see these are all just multiply here. This times this. I mean, I could have put it in that other order as well. Yeah, I could have gone straight across. I don't know why I didn't, just to make it more confusing. On your calculator you did? Okay, let me just check